Welcome to this lecture series in linear algebra. In this lecture, we'll prove an interesting divisibility theorem about the dimension of certain subspaces. And let us recall what we need. So we defined the notion of a cyclic subspace. If T is an endomorphism and V is some vector in the vector space, then the cyclic subspace generated by V is defined as the linear span of all these vectors. Right? And we saw that one way to describe the cyclic subspace is this expression. Alright? And then we proved a nice representation theorem about cyclic subspaces, meaning there is a canonical way to express any vector in a given cyclic subspace. We don't really need to know the theorem, we just need to know a very simple consequence of it, which is that if we have an endomorphism on a vector space V and Px is an eigenpolynomial of T, then for any vector in the kernel of Pt, so we do not need to consider generalized polyenvectors for this particular bullet point, just any polyenvector V corresponding to the eigenpolynomial Px, the cyclic subspace of V generated by, the cyclic subspace of capital V generated by this vector little v is this thing. So you consider all such, vectors where Qx is a polynomial over the base field, of course, but with this degree constraint. So it's an immediate consequence of the second bullet point, but you can prove it directly. You don't need to know any theorem or anything, just this fact and a little bit of thought will give you this. So this is all that we need to know. Of course, we will need generalities like quotient spaces and, just general linear algebra that we have been using throughout. So let's not recall that. Let's move on. Here are two problems for practice. And now let us get started. So first we will prove a decomposition theorem about kernels of endomorphisms coming from eigenpolynomials. So fix an endomorphism T and let's say Px is some eigenpolynomial of T. Then one can find finitely many vectors such that the kernel of Pt can be expressed as the direct sum of the cyclic subspaces generated by these vectors. So of course, even though I've written that there exists V1 up to Vk in the space capital V, if you have to satisfy this equation, these V1 up to Vk have to come from kernel of Pt, in fact, because of course, if this is contained in kernel Pt, then clearly V1 is also contained in kernel Pt. Okay. So it's not a very difficult thing to prove, but perhaps the way I'm going to express the proof, it may look a little bit technical. All right. So here is a starting point which we need to understand. So let K be the largest positive integer such that one can find non-zero vectors in kernel of Pt with the property that, or satisfying Okay, so let's try to understand what I'm saying. First of all, since this is an eigenpolynomial, this is a non-trivial subspace. So you may pick any non-zero vector and create the cyclic subspace generated by it. And then clearly for that particular vector, this equation is trivially satisfied. It's just one vector. So this side would be just the first term and this side would also be just the first term. So this is trivially satisfied. So what we are saying is find the maximum number of non-zero vectors you can find which satisfy this. one can object, why should such a maximum number exist? Maybe you can find larger and larger such lists such that this is satisfied. Well, no, because each of these have dimension at least 1, because they are non-zero vectors, so their cyclic subspaces are also non-trivial. So the dimension of this being a direct sum is at least k. So you cannot have an arbitrarily large list with this property, because this has some finite dimension. So basically this says that since we want to express this as the direct sum of cyclic subspaces, this says just do your best. Find the largest list with this property and hope that this actually is equal to kernel of Pt. And if this is not equal to kernel of Pt, we will arrive at a contradiction which will prove the theorem. Okay, so let's call this thing something for easy notation. So we will call this zk, and we will show that this zk is actually equal to kernel of Pt, and that will finish the proof. Okay, so we will proceed by contradiction. So suppose not, give me a second. Yeah, suppose not. Then one can find some vector in the difference, right? So let me also point out that clearly this is contained here. This containment is obvious. So if we assume that this equality, if we assume that this equality does not hold, that means that this is strictly contained, and we have just picked something which is away from this guy. Okay. Now, by the maximality of k, we have this cyclic subspace intersects this guy non-trivially. Because if this intersection was trivial, you could append little v to this list and preserve this property, and that would mean you have a larger list than of length k. So we have this. Okay. So one can pick some non-zero vector here in this intersection. All right. And now since little u is here in particular, we can find some polynomial with degree being less than the degree of px and u being equal to this thing, right? And here let me remark that one should note qx is in fact non-zero. Qx is non-zero because if it were 0, then qt would be 0, and hence this would be 0, and hence u would be 0, but by choice u is non-zero. Okay. So in particular, this means that this is in zk because little u is in zk. And now we will use Euclid's theorem. So since qx is a non-zero polynomial with degree less than the degree of px, and px is an irreducible polynomial being an eigenpolynomial, we know that px and qx are relatively prime. Okay, so we will use Euclid's theorem So by Euclid, there exist two polynomials ax and bx such that which implies this is the identity thing. And now what we do is we operate this both endomorphisms on V. Whoops. Right. This left-hand side was an endomorphism when we had not written this orange V. So all we do is that the left endomorphism we operate on V and the right one operate on V. So on the left side we get this and the right side we get that. But little v was in particular chosen in the kernel of PT. Right? Little v was chosen in kernel PT, and hence this is 0. And this is of course V. So what we get is, so we have that. But then from this equation, thus BTQTV, which is equal to V as we just saw, is also in ZK. So this was in ZK by the previous slide, but since ZK is T invariant, this is also in ZK, but this is equal to V. So we see that V is in ZK, and this is a contradiction. Because our choice of V was that V was away from ZK. All right. So this proves our theorem that you can write kernel PT as the direct sum of a certain number of cyclic subspaces. Okay. So this has a simple corollary, because the dimension of every cyclic subspace generated by an eigenpolynomial, sorry, what am I saying? The dimension of the cyclic subspace, ZVT, for any generalized polyeigenvector V is divisible by the degree of the polynomial. Right? So this is something that I kind of glossed over in the recall. So perhaps let's go to that. So here this big theorem in particular says that the dimension of the cyclic subspace generated by any generalized polyeigenvector is divisible by the degree of the polynomial. In fact, it depends on precisely the smallest k for which this equation holds. So anyway, just recall this theorem, and hence you will see that each of these have their dimensions divisible by the degree of px, and hence the dimension of this is also divisible by the degree of px. So an immediate corollary of the previous one is that if you have an endomorphism and some eigenpolynomial of it, then the degree of the eigenpolynomial divides the dimension of the kernel of this endomorphism. Okay, so this is important. And now, here is the main point that we wanted to prove. So we will just generalize this previous slide. Fix a positive integer, then for any endomorphism T, and for an eigenpolynomial Px of T, the degree of Px divides this guy, the dimension of the kernel of Pt to the power m. So this is extraneous. Yeah. So this is what we want to show. Okay. So this will be done by induction on M. What does that mean? It means that suppose you have somehow proven this statement for some m. So fix an m, and suppose you have shown that whenever you have an endomorphism with px an eigenpolynomial, then degree px divides this guy, then we will prove it for a bigger m. just one value higher. That's how inductions are done. Okay, so the base case was the previous slide. Base case was m equals 1. That was the previous slide, so it definitely holds. So let m greater than equal to 2 and assume that the theorem is proven for all smaller values of n. Okay, and yeah, so we want to prove for this particular m. So one reduction we will make is a very simple one. We will define this endomorphism, right? This is a T-invariant subspace and we are just restricting our endomorphism to that. So, well, technically I should write this entire thing that let T be an endomorphism and Px an eigenpolynomial, right? And now we are defining, and maybe one more line would be helpful. We want to show that degree Px divides this dimension. Right, so that is our setting, and now we define capital S as this endomorphism. Since this is a T-invariant subspace, this is legitimate. And here, note that. I mean, this is a trivial thing that I'm going to write. Px is the only eigenpolynomial of S. Right? Why is that? Because if you just think about it, kernel of Ps to the m is nothing but kernel of Pt to the m. So kernel of Ps to the m is actually the entire domain of S, because this is the domain of S. And hence, every vector in the domain of S is a generalized polyeigenvector corresponding to this polynomial, and therefore that can be the only eigenpolynomial, because generalized polyeigenvectors form a direct sum decomposition of any vector space. So just realize this fact. I mean, I'm not saying this in too much detail, but this should be, if you followed the previous lectures, this shouldn't be a hard thing. Okay. So in particular, I mean, I've already said this, but in particular, we have, note that. Right? So maybe I'll argue this thing. I said this for any arbiter for m, but this is true for any k. So suppose something is here, meaning pt of that vector is 0. Then whatever that vector is, it's going to lie here also. And hence you can apply s to that vector. But if you apply s to that vector, what you get? It's the same as, or you can apply ps to that vector because it's here. But applying ps to that is same as applying pt to that. So yeah, so this holds. And this is an S-invariant subspace. Clearly, kernel of ps is an S-invariant subspace. So maybe just one more line I will write and then proceed. Yeah. So this also I leave you to argue. So yeah, so this is an S-invariant subspace. So we can make this diagram as we always do whenever we are dealing with quotient spaces. Wasn't really necessary, but I like to draw this. Okay, here this pi is your natural projection homomorphism. And I mean the natural projection linear map, let's not call it homomorphism because we just did not introduce that terminology. Okay, so here is the main point. We claim that this quotient space is actually equal to this, right? So this containment is obviously there. This is your domain of S bar, and hence anything here automatically lies here. But we want to say that actually this is an equality. So let's give a proof. So pick something in the left side. Where we some arbitrary thing in this sky, right? So an arbitrary element here looks like this, where little v is just some arbitrarily chosen element here. So therefore, this is 0 just by this fact, which implies Ps of Ps to the power m minus 1 of v is 0. Right, clearly. And therefore, this vector is the 0 vector in the quotient space. This is a vector in your in the parent space, but now you apply the natural projection map to this, so you get a bar, and this I mean something lies in the kernel of Ps, meaning the thing that you're quotienting by, if and only if the image of that something under the natural map is the 0 of the quotient space. We are not saying anything out of the ordinary. But again, as we have seen many times, this bar is actually the same as this thing. It's a simple check. So this was a vector in the top, meaning here. We apply the natural map to get something here. But alternately, what we can do is we can first apply the natural projection and apply this endomorphism on the thing when you apply this endomorphism on v bar, where you know the meanings of all the terms. So just check that this is equal to this, and we have done this before many times, in fact. Okay, but just this implies that v bar is in the kernel of, and this is all. This proves the claim. We started with an arbitrary vector on the left side. We ended up showing that it is on the right side, and hence the claim is proved. Okay. So we finish by applying the rank nullity theorem to pi. So recall pi is this map, natural projection map. We get dimension of the kernel of pi plus dimension of the image of pi is the dimension of the domain of pi, which is this quotient space. Which is this kernel of Ps to the power m. All right. But what is the kernel of pi? Of course, it is the space that you're quotienting by, which is kernel of Ps or kernel of Pt, whichever you like to write. Dimension of image of pi is clearly this quotient. Which is equal to dimension. Yeah. So what is Yeah, so let's just use this claim here. So we get okay. So we just need to say one more thing. We want to say that Px is an eigenpolynomial of S. Px is an eigenpolynomial of S bar. So this is what we want to say. Why is that? The only eigenpolynomial of S was Px, as we noted. Okay. So the only candidates for eigenpolynomials for S bar are just Px, because eigenpolynomials of S bar will divide the minimal polynomial of S bar, but minimal polynomial of S bar divides the minimal polynomial of S, and hence they will also divide Px. So the only the only candidate for an eigenpolynomial of S bar is just Px. Okay. So as long as this quotient space on which S bar is an endomorphism on, as long as this quotient space is non-trivial, Px has to be an eigenpolynomial of S bar, right? So in the case where this is a trivial space, meaning this is actually equal to that, there is nothing to prove. We were already done. So all this argument was needed when this is actually a non-trivial space, and hence Px is an eigenpolynomial of Px is an eigenpolynomial of S bar, and therefore by induction on M, this is divisible by degree Px. Right? This is a smaller value than M, and hence by induction, this is divisible by degree Px. In either case, even if this were a trivial subspace, the argument still goes through. We do not need to add any extra lines, because if this is the trivial subspace, then this is also the trivial subspace, and hence this is 0. And 0 is obviously divisible by degree Px. We do not need to add anything extra to the proof. I'm just saying that in case this is a non-trivial subspace, Px is an eigenpolynomial of S bar, because there are no other candidates for eigenpolynomials. Okay, and hence you can apply induction to show that the degree of Px divides this, and hence the left side is divisible by degree Px, and hence the right side is divisible by degree Px. And that finishes the proof. That finishes the induction and hence the proof. So just one more line, degree Px divides dimension, which is nothing but dimension kernel Pt to the power m, and we are done. So it may seem like a complicated thing, but it is not. Just stay on this proof if it is unclear. Okay. So a corollary of this is that if you have some endomorphism and some eigenpolynomial, then the degree of the eigenpolynomial divides the geometric as well as the algebraic multiplicities of the eigenpolynomial. This is an immediate corollary of the previous slide. Okay. We will say a little bit more in the next lecture, in which we will prove a version of the Cayley-Hamilton theorem. But for now, this will serve us well enough. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.